right? So we can have the W equation. W adiabatic is equal to 1 by 1 minus gamma into PF VF minus PI VF. Right. Just go through the derivation. That was easy one only. Just you have to substitute the values for. We have to integrate. Then we can get the value for W adiabatic. That is 1 by 1 minus gamma P final V final minus P initial V initial. Then also we know we can substitute and get W adiabatic mu r by gamma minus 1 T initial T final because PV is equal to T. Right, PV is equal to mu r T. So we can have P final V final is equal to mu r T final, and P initial V initial is equal to mu r T final. And mu r is a constant, so we can take outside. So finally we can get the equation W adiabatic as mu r by gamma minus 1 T initial minus T final. Right. Yes. That is T final minus T initial. Then, so this is the PV diagram of adiabatic process. So look at this diagram. So there is a two isotherm. Isotherm is in the sense that is two different temperatures. So there is for P initial, B initial, T initial. There is one isotherm. There is one temperature. For P final, B final, T final, there is that graph in another temperature, another isotherm. So for adiabatic process, there will be a change in all the three parameters, all the three functions. So just keep in mind. So to differentiate between isothermal and adiabatic curves, the adiabatic curve is drawn along with this isothermal curve for TF, TI. So if there is a isotherm, then we can identify that process is an adiabatic process. Then we can also identify with the steeper curve. So if the curve is steeper, then we can identify that process is adiabatic process. Then go to the next process, isobaric process. The equation will be same. So we have to derive Q. We have to derive equation of state. We have to derive Q, and we have to derive the value for W. Right. So the next process is isobaric process. You know, isobaric in the sense pressure will be constant. So we can have the equation PV is equal to mu RT as here volume is constant. So sorry, pressure is constant. So we can take mu R by P as constant. So we can get the equation is equal to T. So if you increase the volume, then we can get the increased temperature. If you decrease the volume, we can get the decreased temperature because that is directly proportional to V and T. Then we can have the equation of state as V is directly proportional to T. So this is the equation of state for adiabatic isobaric process. Then we can draw the BT graph, that is volume versus temperature graph. But that graph will show you straight line passing through the origin. If a gas goes from initial state to final state at constant pressure, then the system satisfies the following equation, that is V by T. It is T by V. So we can write so V initial by T initial is equal to V final by T final. Right. So T by V is equal to T by V. So T final, V final, we can substitute the equation. Okay, so V by T or T by V can be written. Right, so this is the equation of state for two different states. Then these are the example of isobaric processes. When the gas is heated and pushes the piston so that it exerts a force equivalent to the atmospheric pressure due to gravity, then this process is isobaric process. So the first figure show you the isobaric process in piston cylinder arrangement. The masses maintained at constant pressure in the cylinder. So these masses were provided to keep the system with the pressure constant. So if you adjust these masses, then we can get the system constant with pressure. Then most of the cooking processes in our kitchen are also isobaric processes. When the food is cooked in an open vessel, the pressure above the food is always at atmospheric pressure. So this is an open system. Actually, this cooking is an open system. The atmospheric pressure will be same throughout the process. The T here is constant. So these are the examples of isobaric processes. Then we can look at what is how will be the PV diagram of isobaric process. Then pressure is constant here, so the curve will be straight line, that is the horizontal line, because P here, right? So during a compression, the volume gets decreased, final volume will be more, the initial volume will be less, and during expansion, the volume will be increase. So V initial and V final will be differ. As you look at the PV diagram of isobaric process, there will be a straight line, right? Then we can calculate the work done. So how can we calculate? By integrating PdV. So W can be found by integration of PdV. Then we can substitute the value for P here. So P here is constant. Then we can take P outside. Then there is only integration of dV. So integration of dV can be written as P into V final minus V initial. So we can have W as a P delta V. Delta V in the sense change in volume, right? So we can calculate the work done by an isobaric process by using this equation. W is equal to P delta V. So delta V is a change in volume, right? Then next step is to find the work done. So we know the equation PV mu r T. From that we can have V is equal to mu r T by P. Then if you substitute in the above said equation, we can have mu r T final into 1 minus T initial by T final. So just try to substitute the values in this equation. That is P, W is equal to P into V final minus V initial. Then we can then take the common terms outside, and we can have this equation is equal to mu r Tf into 1 minus Tf by Ti by Tf. So this derivation is given to you. Just derive this equation by substituting the value in the equation of this one, 8.48. Then we can have this equation. In the PV diagram, the area under the isobaric curve is equal to the work done in an isobaric process. So we know all the process from the PV diagram. We can have the work done. So if you substitute this W, if you compare the first law of thermodynamics for this process, we know delta U is equal to Q plus or minus W. So we can substitute the W value here. That is P delta V So then we can have another equation of first law of thermodynamics. Then just then we can try to solve this problem by using the above formulas. Let's try to solve this problem. Let's take 5 minutes and read this question and get some idea to how to solve this problem. Just read this problem 2 times. 1 mole of an ideal gas initially kept in a cylinder at pressure 1 megapascal and the temperature 27 degrees Celsius is made to expand until its volume is doubled. Right. So the process, we have pressure, then we have temperature, then we are doubling the volume. So V initial is V final is 2 times of V initial. Then the questions were how much work is done if the expansion is adiabatic process, isobaric process, and isothermal process. So there is a question with all the 3 processes. So we have to know all the 3 equations, all the 3 processes equations. We have to know the equations of adiabatics, isobaric, and isothermal. So we have to use all the 3 equations. Then this equation will be identify the processes in which the change in internal energy is least and it is maximum. So just you have to find the change in internal energy delta U by using the first law of thermodynamics. Then the third question, show each processes on a PV diagram. So adiabatic process, isobaric, isothermal. We have to draw the PV diagram. Then name the processes in which the heat we have to give the values for Q. Okay. In the PV diagram, we have to mention the isotherms. Right. So just try to solve the problems one by one. So we have the values of T1, we have the value T1, and we know the volume is doubled. V initial, V final is equal to 2 times of V initial. And first question is how much work is done? The expansion is adiabatic. The solution is here. So in an adiabatic process, the work done by the system is W adiabatic is equal to, you know, the formula by gamma minus 1 into T initial minus T final. Right. So to find the initial temperature, we can use the adiabatic equation of state. That is T final V final power gamma minus 1 equal to T initial V initial power gamma minus 1. Adiabatic process, we can use this equation, then we can find the T final. So here only T initial given, so we can find the T final by using this equation. Then that is 189.8 Kelvin. So if you substitute the values, then we can find the T final value. That is 189, approximately 190 Kelvin. Then we can substitute the values in the equation of W. So we know the mu value. Mu value is given 1 mole. So mu value is given 1 mole. Then we know the R value, universal gas constant 8.3. Then gamma minus 1. So we can have gamma values. How can we get the gamma values given there? So take gamma is equal to 5/3. Then the temperature. T initial is given and T final were calculated. Then if you substitute, then we can get the value of W 1.37 kilojoule. 1.37 kilojoule in positive. Then we can move to the next process, isobaric process. So isobaric processes, we know the value for W, P delta V. So we can change, we can substitute the values. We know the value P, and we know the values of V initial and V final, that is 2 times. That is, then we can have the equation of W. Wait a minute. Hello. Hello. I'm Ketra. I'm Solomon. Right. So this we can have the equation W is equal to T to P V initial. So we can find the V initial by using the formula P initial is equal to R T initial. So P is equal to mu R T, we know. So mu here is 1. So we can have P initial, V initial is equal to R T initial. So we can substitute the values. So P initial 1 megapascal. Then we know the T initial value. Then V initial values. R value of R. Then we can find the value of V initial. So V initial will be 24.9 10 to the power minus 4 meter cube volume. Right. Then the work done can be calculated by using the above formula. W, we know the value of pressure T. Then we can have the value. We found the value of V initial. And if you substitute, we can get the value of W, that is 4.9 kilojoule. Then move to the next process, isothermal process. Then we know the equation of state. Then the equation for W, that is mu R T ln P by V initial. So we know the value of mu, we know the value of R, we know the value of T, we know the value of P final, V initial. Then we can V final, then we can substitute, then we can find the value for W as 1.7 kilojoule. Right. So the next question is comparing all these all three processes. We see that the work done in an isobaric process is greatest, work done in the adiabatic process is least. So if we compare these three above work done, so 1.7, 4.9, and before that. So comparing all these three, we can get the work done in an adiabatic process. First process is greatest, and work done in the adiabatic, the isobaric process is the greatest, and work done in the adiabatic process is least. Then the next question is to draw a PV diagram. So we can draw like this. So we can have the x-axis P and the x-axis V and y-axis P. Then the curve AB, AC, and AD. So AB is isobaric process. The isobaric process, so pressure is constant. Then we can get the straight line. Then AC, the curve AC will give that is isothermal process. Then the curve AD will give you the adiabatic process. We compare these two curve with isothermal and adiabatic. The adiabatic process is steeper than isothermal curve. Right. So implying that the work done in isobaric process is highest, and work done in adiabatic process is less. Just we know the area under the curve will give you the work done, right? So area under the curve will give you the work done. So the area will be more for isobaric process. So the isobaric process will give you more work done. Then the area under the curve of adiabatic process is less here. So that will give you the less work done. And so, it's on. Then the fourth question: in adiabatic process, no heat enters into the system out of the system. In isobaric process, the work done is more. Why it happens? Because there is no way to transfer heat. So you can answer the fourth question. Then these are the applications of equations of states and the equation of W and first law of thermodynamic equations to solve these kinds of problems. So the formulas can be used to solve these kind of problems. Then we can move to the next process, isochoric process. You know, isochoric in the sense constant volume. Right. So in the PV diagram, we can get the straight line, that is horizontal straight, because V is in x-axis, so the volume will be constant throughout the process. So during expansion, there is no expansion and compression. We can increase the pressure and we can decrease the pressure during isochoric process. Right. So the equation of state for this process is, again, we have P is equal to mu RT. So volume here is constant, so we can take volume to the next on the side. So we can have P is equal to mu R by V into T. So these three terms, mu R and V is constant. Then we can take P is equal to T. Right. So E equal to T. Then we can have the equation of state for two states, that is P initial by T initial equal to P final by T final. Then this is the figure of isochoric process. So the volume is kept constant. Then we can increase the pressure by adding heat, and we can decrease the pressure by releasing heats. So this is the example of isochoric process. Volume is kept constant. So the cyclic tire. So the air-filled cyclic tire is the example of the isochoric process. The volume of the system is constant. Then we can use the first law of thermodynamics. Here delta V, change in volume, is 0. So the W value also will be 0. So W value will be integration of P dV. So here delta V is 0. So W value also will be 0. Right. So then we can substitute these two values into the first law of thermodynamics. Then we can have the equation of first law as delta U is equal to Q alone. Right. W will be 0. Suppose a system loses heat to the surrounding through conducting walls by keeping the volume constant, then its internal energy decreases. As a result, the temperature decreases, the pressure also decreases. So by using conducting walls and keeping the volume constant, then the internal energy, the change in internal energy decreases. If temperature decreases, the pressure also will decrease. So if you provide heat to the system, the internal energy will increase, and if you release the heat energy, then internal energy will decrease. So equation, internal energy is directly proportional to Q. So if you increase the internal energy, if you increase the heat, then we can have the increased internal energy. If you decrease the heat, we can have the decreased internal energy. So because the two terms were in directly proportional. Then these are the examples. So when food is by closing with the lid, as shown in figure, when food is being cooked in this closed position, so this is a isolated system. Sorry, closed system. So take this closed system. Then if you add, if you supply heat energy to the system, then the pressure inside the internal energy inside the system will increase. Then the pressure will increase. So because of that, the volume, the lid will try to open. Then the next example. So in automobiles, the petrol engines undergoes 4 processes. First, the piston is automatically compressed. So this is the first process. So adiabatic compression will happen. So how can we achieve adiabatic compression? Then compression, right? Then in the second process, the volume of the air fuel mixture is kept constant and the heat is being added. So in the second figure, the volume will be constant. Then we will fire this gas by spark plugs. Then the second process is isochoric process. So volume get constant. Then third process, adiabatic expansion. So first process adiabatic compression, second process isochoric process, and third process adiabatic expansion. Then the fourth process again isochoric process. So we can have the third and the fourth process is isochoric process. Isochoric in the sense we have to keep the volume constant, right? So these are the examples. Just try to understand. Then you can solve one example by using the isochoric process, I think. Yes. Just try to solve this example. 5 gram of water is heated from 30 degrees Celsius to 60 degrees Celsius. Ignoring the slight expansion of water, calculate the change in internal energy of the water. They gave a specific heat of water 4184 per Kelvin kilogram. Kilogram Kelvin. So the given data where, so we can have the mass 500 grams, then we can have a temperature T initial, T final. Also they stated ignore the slight expansion of water. So just we can neglect the expansion of water, and we have to calculate the change in internal energy. So we can get this process is isochoric process. So when a water is heated from 30 degrees Celsius, 60 degrees Celsius, there is only a slight change in its volume. So we can treat this process as isochoric process. So this process is the isochoric process. The volume is constant here. Then in an isochoric process, the work done by the system is 0. So we know the equation of states. So we know the Q value is 0 here, and the W value is 0 here. Then the given heat supplied is used to increase the internal energy alone. So delta U is directly proportional to Q. So we know the equation delta U is directly proportional to Q. So we know the value for Q, that is M SV delta T. So Q equation Q is equal to MSV delta T. That is SV is specific heat capacity of the water with constant volume, right? SV. So the SV value is given there. So we can substitute and find the value of Q. So if you substitute the mass values in kg and the temperature, 30 temperature in Kelvin, then we can find the value for Q, that is equal to the value of delta E. So the internal energy here is 62.76 kilojoule. So we can calculate by using the equations. Just keep the equations. Just keep the equations in mind. Then the next slides, already we discussed this slide. So these are the comparisons of all the 4 processes available in thermodynamics. So we can get the comparison by seeing this by seeing this figure. So these are all the 4 processes. So isothermal, isobaric, isochoric, adiabatic. So we can have isothermal expansion, isothermal compression, isobaric expansion, isobaric compression. Then we can have adiabatic expansion and adiabatic compression. So every process PV diagram were stated that. So also we were provided done equation for all the processes. W formulas were compared here. Then the functions of the pressure, volume, then Q, also temperature and internal energy also compared here. So if you look at this figure, yes, you can get some more idea about all the 4 processes. Just keep in mind you have to we have to clear about the equation of state and the functions of the states and what is the work done in the processes. Then PV diagram. So if you look at this slide once again, you can compare all. We can easily mug up all the 4 processes. Just try to familiar with this figure, right? So I think we can stop. So just try to learn in these processes. So that's it. So today class is over. If you have any queries, you can wait and ask, or else you can hang up. Thank you. Have a good day. Any questions, Tama?